Shall we start? Mayanka is there?
Yes.
Oh, okay. So should I share?
Yep. Please go ahead.
Right. So last time we stopped at section 9.7, nonlinear function approximation, and so we should start with discussion of application of artificial neural networks to reinforcement learning for function approximation. And in general, neural networks broadly can be referred as nonlinear functions, and I think in current understanding, basically any nonlinear function can be referred as a neural network. So before we discussed linear methods, and linear methods are good with respect to the fact that they are well studied, have lots of nice properties, and are well understood, but there are certain problems, and probably the main problem which kind of made the neural network so popular in machine learning nowadays is that linear methods rely on they have a limited expressivity, and for those to work well, we need our feature space to be linearly separable, and this is not the case in general. So to make linear methods work well, we need to construct such features that our space will be linearly separable, and it might require a lot of domain knowledge and handcrafting, and yeah, it's really hard problem. It cannot be solved like in any kind of general setting. So when using neural networks, we obviously avoid this problem by like putting this work into network itself. So the neural network has some inner hidden representations of the data, and it is supposed to find a good representation which is which transforms our data in a way that it is useful to produce the desired outputs, and the representations are learned. Yeah, on the other hand, when reading this chapter, I've kind of catch myself with this thought that we really don't understand so many stuff about how this all works, and so many choices are kind of arbitrary or are made based on some random discoveries or some restrictions we have, rather than on the based on some strong theoretic ideas or something like that. So yeah, let's go through this chapter. I think everyone knows what neural network is in general. So here we have very basic multi-layer perceptron. It has like two hidden layers, and so this would be just fully connected network, and we need to have some nonlinearity between layers to make this function nonlinear. Otherwise, no matter how many layers we stack, we will still have a linear function. Okay, and yeah, so here the authors mention some popular choices for nonlinearities. So we have sigmoid, which is currently not used in like as an activation function. Commonly, it only used in binary classification as output nonlinearity, or in some gating layers where we want to compute some, gating coefficient. But otherwise, we are now mostly using ReLU, which is here. Yeah, it's 0 if input is negative and input itself otherwise. I hope everyone is familiar with a lot more of different activations functions which are used nowadays. Yeah, so sometimes hyperbolic tangent is useful, and it is used in many networks. Also, now we have some variations which are similar but have some different properties and kind of similar to ReLU but have some different properties. So like GLU surface, which is kind of a smooth, like differentiable everywhere, and it's often used in transformers. There is self-normalizing units, which have like preserve the mean and standard deviation, but they are also not very often used nowadays. I think they were designed for fully connected networks. So there are a bunch of choices, but good old ReLU, maybe leaky ReLU, is most often first choice today still. Okay, and so that would make a neural network like interesting in terms it is composed of very simple building blocks, but the complexity arises from this composition of a bunch of layers. Okay, so here they mention as a how it's called, the let me find the name. Yeah, so this famous theorem which states that neural network with a single layer can approximate any continuous function on a compact region to any degree of accuracy. That's a very kind of famous theoretic result, which is very impractical in terms. Yeah, so we can. So this universal approximation theorem, it states that neural network can approximate anything, but we don't use it anywhere in general. So because usually neural network benefit a lot from stacking layers, so making the neural networks deep. And this aspect is not well studied theoretically as well. Yeah, so we're probably when we go to some of the techniques they mention here, we will have a chance to talk about it a bit. So that would be, I believe, another chapter dedicated to applications of neural networks to reinforcement learning with examples. I think it's chapter 16, so we will get to that. Okay. Yeah, so the neural networks, as I mentioned, they build an internal representation of the data and use that to produce the final result. And ability to find this useful internal or representation is what makes them so useful. Okay, so usually we learn the weights of neural networks with backpropagation using some stochastic gradient descent and its descendants. So as a and one thing to think about here is the fact that we are using backpropagation is somewhat limiting in terms like, for example, sometimes so again, the neural networks can approximate any function, but we are not guaranteed to find the best possible approximation using gradient backpropagation with gradient descent in all cases. And before some engineering improvements were introduced, the neural networks were failing in many cases, but obviously a lot of work like engineering effort is put into them today, and the results are really good. So therefore even more effort is put, and so the result improved. So that's a hot field right now, and it also in context of reinforcement learning, some of the most impressive results are heavily relying on neural networks. And yeah, I'm talking about this results from DeepMind with so they yeah, have really great results with AlphaGo, AlphaZero, MuZero, and so on. So now they are expanding to like more and more environments, and yeah, that's that is really cool. And neural networks to used as function approximators are important building block of those architectures, together with Monte Carlo research, as we know. Okay, so neural networks are often they have a lot of parameters, and therefore they are prone to overfitting, and we need to address that problem in some way. And yeah, so here the authors mentions that it is less of a problem in reinforcement learning when we learn online. It's unlikely that we will have like we will be able to just end up memorizing examples from training data because we don't have static training set, but still effective generalization is very important for when training neural networks. And there are a lot of techniques you can use to improve the generalization abilities and also to verify that you generalize well. So here they mention a cross-validation when you split your training data and like you have multiple splits of available data into training and validation data, and you want to make sure that your approach works well across all the splits and this helps avoid overfitting to the validation data. On the other hand, with the big data regime, this is not used like really often. So when we really have a lot of data, I think the cross-validation is usually omitted. But still a very useful technique to make sure that you don't like over optimize towards the validation you have. Okay, so also we can have some component in our optimization objective, like we can have a regularization term to restrict the like function space the neural network can approximate, and usually it's kind of like L2 norm or L1 norm applied to the weights, and there are different ways to enforce regularization. So there are sort of don't go into details here, but probably you are familiar in that as well. And another way to reduce the number like of degrees of freedom, or like basically to restrict the expressive ability of our network to force it use learn something useful, is weight sharing, and that might be so that is used in different ways. Like in convolutional neural networks, we have a lot of weight sharing due to the nature of convolutions. We apply the same set of filters across the image everywhere. There are other ways of weight sharing. For example, in some architectures, we apply the same layer multiple times, and yeah, that is used, for example, in different transformer architectures like Albert, if you know it. So there we have like a couple of different layers which are applied multiple times, like in a loop. So okay, so those are the ways to reduce overfitting. Yeah, and a very important method is dropout. And yeah, so the idea is we, with some probability, we have the output of every neuron zeroed out, and in such a way we force the network to kind of have this, to distribute the useful information across neurons rather than having some very specialized neurons. We kind of make it by zeroing out randomly each of the outputs with some probability. We force the network to have like multiple information routes, and this can be another way to think about it is like a training ensemble model in a single so we have a single model, but it acts as an ensemble during training. Okay. Yeah, and here's a mentions important work by Hinton and collaborators on training deep belief networks. And yeah, that was back at the time when training deep networks was difficult. And also what they did, they trained it layer by layer in unsupervised fashion, and by starting with the deepest layers, and then using the output of that layer as an input to the next layer, training it, and so on. So in this kind of recursive way, you can train this deep belief network and then use it as an initialization for the weights. But now this approach is mostly, I think, it is not so popular. So we have ways to train deep networks in like one go. And here they mentioned that with this deep belief networks, the results were the better results were produced than starting with random weights, but I'm not sure if this is still true. So, and one of the important techniques that enabled training very deep networks was batch normalization. Basically, we introduce this batch normalization layer between each of the layers as mentioned above, and we compute the batch mean and standard deviation, then normalize the batch of the data using this batch statistics, and then we apply some learned shift and scale, or scale and shift in that order. And basically this allows, this allowed to train very deep networks, and the behavior was much better. And again, the theory of batch normalization is not like completely understood, I believe. And there are some efforts and results with training very deep networks without batch normalizations, but in general, some kind of normalization layer is a standard building block of modern neural networks still. And there are different variations of normalization. So for example, layer normalization is used in transformers, and there are some more specialized normalization layers like instance norm, which is used in style transfer networks and stuff like that. But the batch norm was first, and I think it's still most popular in convolutional architectures. Okay, another very important discovery which allowed training really deep networks and getting, like, improving their results significantly was this deep residual learning. So instead of learning the transformation of X, we kind of learn residual, which is, so how do we change X in order to get something useful? And this is done by adding a skip connection. So we have some computation, and the input to this computation is added to the output of the computation. In such way, we can kind of at least perform as good as without this layer. So if the computation is identity, then we have just input the same as output, and this allows this is really essential to enable training really deep networks, and works really great in practice. On the other hand, it's not necessarily kind of an always necessary to do, but again, this is what makes this combination of backpropagation and stochastic gradient descent work. So yeah, so this is kind of an engineering trick to make deep networks work. Okay, and again, so convolutional architecture they discuss here. It is so the reinforcement learning applications, famous reinforcement learning applications like AlphaGo, I think, rely on specifically on deep convolutional network, and the idea behind convolution is, or convolutional networks, is this weight sharing, which introduces translation equivariance, I think it's called, to the network, so that the same filter is applied everywhere across the image, and therefore the number of parameters is lower, and so the parameters are shared. The same set of parameters is applied everywhere, and this in this way we introduce useful prior knowledge into the network design and make it much more sample efficient. Okay, but to have use of this, we need to be sure that this prior knowledge we introduce, in this case, it's this translation equivariance idea, that it is applicable to our data. So it is applicable to natural images, but might be not applicable to some other type of data. And there are different different architectures introduce different types of prior knowledge. For example, LSTM architecture would introduce this sequential structure of data, and so we assume that the next input depends on the previous one, and there are like a very popular architecture nowadays is transformers and transformers are operating on sets. So in that case, they don't have a lot of this inductive bias introduced into the model itself, and we expect it to learn all by itself. And given enough data, this approach works very well. So that is kind of interesting, but still, yeah, we need to introduce this positional embeddings for text, for example, in transformers, to let the model know that there is some kind of sequential structure to the input, because the architecture itself is completely unaware of that fact. On the other hand, the convolution here, they are aware. The convolutional computation, it is itself aware of the local structure of the image. Okay. Yeah, so I think that everyone has seen this before. And okay, so if any inputs here, please feel free to jump in and share your ideas. I don't think we need to kind of linger on this image. I think everyone is familiar with this stuff already. Okay. Yeah, so just to mention, the convolutional neural networks were introduced by Jan LeCun in 1998, and that was really one of their first kind of architectures which was really practical, and yeah, produced this nice, impressive results, and kicked off this neural network era we have right now in artificial intelligence. Okay, and again, we will get a lot more into this at chapter 16. So, but another thing to discuss here is that there are some differences between reinforcement learning and supervised or standard unsupervised training we are used to, like in classic or not classic, but just more popular deep learning, and that might have some implications and some impact on how training works. And for example, in this DeepMind lecture, the lecturer mentions that the experiences from which we learn in reinforcement learning setting are not independent and identically distributed. So there is some correlation between the experiences we present to neural networks, and that is different from what we have like in standard supervised setting, right? So this is not necessarily a problem, but in some way this might have impact on how the training goes. And yeah, I'm not really very well familiar with this, but I think oftentimes they have some kind of teacher-student approaches, or maybe so. In reinforcement learning, when some weights of the neural network are updated, so we have like online weights and this mean weights, and yeah, hopefully we will get more into that when we will be considering particular applications of deep neural networks for reinforcement learning. Right, so that's my take on this nonlinear function approximation chapter, and feel free to add your thoughts here. Okay, and now we can move to something that is a bit different from that. So back to the linear methods. We had last week we had discussed this TD0 method with function approximation, and we find out that it converges to fixed point given as a product of expectation of these two factors. One is given as this outer product of two vectors here, and which produces some matrix, and let's denote it as A, and the expectation of rewards times, so X here is our feature vector, and here you can see that it has some time indices, and which denotes corresponding states that produce this feature vector, and the state is like to correspond to some time step. Okay, so the fixed point here would be for the weights of our function. So we have some linear function approximation, and we have this weight vector W, and it is converging towards this fixed point given as A inverse times B. Okay, and one idea here is that instead of computing this solution iteratively, we can be much more data efficient by computing the estimates of A and B, and basically using this computing this fixed point directly instead of going to through this gradient descent procedure towards the solution. And this can be done, and this is called least square STD algorithm, LSDD for short. And in this case, we are using this approximations to A and B for given time step t, which is computed based on the experiences we had so far, observations we had so far up to time step t, right? And this expectation can be written as a sum from 0 to t minus 1 of this outer product plus some small epsilon multiplied by identity matrix to ensure that A is invertible, because we need to have an inverse of it to compute our solution, and B can be computed as this sum as well. And you may note that we should to have this expectation here, we should have divided by t, but since we are going to here we are going to multiply A inverse by B, this 1 over t would cancel out. So therefore we can just omit it. And with that, we have this closed form solution for the W sub t. And so, okay, that is great. We have like our best possible solution using experiences up to time step t. Why don't we always use it? Because of computation complexity. So the TD0 was order D, had computation complexity of order D, where D is the dimensionality of our vector, feature vector, and the weight vector as well in this linear case. And so what would be the complexity of this LSDD algorithm? And it is order d squared, which is for high values of d much worse than OD, right? And the naive approach, so here we need to invert a matrix, and that is order d cubed computation, but we can use this Sherman-Morrison formula to, instead of updating our A sub t at each time step and then inverting it, we can compute the, so we can update inverse right away. And the inverse update is given like this. So here we can compute A hat sub t inverse from the x, from like starting with A hat in sub t minus 1 inverse, and updating it using this newly observed state and getting it feature vectors here. So and using this formula, we still have this outer product here, but in this case we can have order d squared computation. And yeah, so that is that is computationally efficient, or this is data efficient, but depending on the computation available, you might be capable or not of using this method. And another thing here, we don't have like a learning rate parameter to tune, like we usually have when using gradient-based optimization methods. And it's not trivial to tune a learning rate properly, and we need to have some when using a gradient descent. So for it to So for have this guaranteed convergence, we need to decay it in some way, and that is not always trivial to select proper learning rate and decay schedule. But here we don't have this, so we just compute the solution directly. But instead we have this epsilon parameter, which is necessary to make sure that the matrix A can be inverted. And in this approach, we use it when setting the initial value for A hat. So we set A hat sub 0 to be equal to this epsilon times identity matrix. And so when we choose it epsilon to be too large, the learning is slow. But when we choose it too small, this we have kind of high variation in our sequence of inverses. So that so selecting this hyperparameter, it can be tricky as well. Okay. And again, we in this case we use all our experiences like equivalently, but it might be not always desirable. So here they mentioned that in control applications, this is typically combined with some other mechanism to induce forgetting. So and that will kind of counterbalance this advantage of the fact that we don't have this learning rate to tune. Okay, and here is an algorithm for this LSDD. And here you can see that it's quite straightforward. So we have our feature vector X, and it's d-dimensional. And we set it such that the feature vector for terminal state would be a vector of zeros. So that can be used to enable us using it in this episodic fashion when we have a terminal state. Okay, so we, as mentioned, select some value for epsilon, then we initialize our A inverse and B. So B we initialize to zeros, and A inverse we initialize to this identity times, or in this case, divided by epsilon. And then we just iteratively update our inverse matrix here. You can see that we can avoid computing the full outer product in this case. So first we compute this value vector V by multiplying A inverse transposed by X minus gamma X prime, where X prime is our next state. And then we update our inverse matrix and set update our B matrix and set the weights to be a product of these two. All right, and in this way, we just loop through all the episodes, and in each episode, we do this computation after each step. Okay, so that is LSDD algorithm. A nice approach, interesting to see how you can approach the optimization problem in different ways, and yeah, probably useful in some settings when you have manageable dimensionality of your feature space, and you want to apply this linear method for learning. Okay, any questions or comments regarding LSTD? Check the chat. Okay.
I guess everything is clear.
Yeah, I was just checking, opened the chat just to have it in case something comes up there. Cool. So next section is about, so we will discuss different approach and alternative to parametric function approximation. In parametric function approximation, we define this mapping determined by some parameters we tune to produce given some state S. We want to get certain value for it. What can we do instead? We can use a memory-based function approximation. In this case, we just memorize our experiences, and when we need to produce a value for a certain state, we will take the state, look up into the memory, and fetch the values that correspond to the most similar states. So let's formalize it a bit. So the simplest case of memory-based function approximation is just like nearest neighbors approach. So if we need a value for certain state S, we can take k nearest neighbors, judging by using some metric function or similarity function, and take the value for that state to be an average of those k nearest neighbors, or weighted average, and we can weight the values of corresponding states by the distance, by the normalized distances, so that we have like this normalized weighted sum. Okay, so here they mentioned that fact that's the simplest case when we just select a single nearest data point from our experiences and use that for our state. But obviously, we should expect some better generalization for some value of k, where we get this weighted average, where we take a multiple closest neighbors and use those to compute our weight. And there is another even more elaborated way to approach this. So locally weighted regression. So we will, or maybe that's not it. So we can basically fit a surface or hypersurface to our local neighborhood and take the value as kind of evaluate that surface at certain point and take that as a value for our state. And that would be kind of the most elaborated approach for nearest neighbor. So in this case, when we are using the non-parametric memory-based approach, we need some distance metrics in the first place. And so some obvious limitation of this approach is that we need to store all the data we want to use for our predictions, and the computational complexity of this algorithm grows with number of experiences we had, and the higher dimensionality of the space is the more kind of complex this lookup. Obviously, this is really this can be really costly to apply when we have like high dimensional state and a lot of experiences we want to use for a lookup. But there are some ways to avoid this problem. So there is an algorithm called KD tree search, which will fetch the most relevant or closest neighbors from our database in a faster way by basically structuring our space in a way that it can be kind of searched in a similar way to binary tree search when we have this logarithmic complexity. Okay, but yeah, so here we don't go into details of these methods and like particular applications, but they mention they have some useful links in the in this references section. Okay, and yeah, so obviously this memory-based approaches have some benefits like that it's a really good way to use your data, but on the other hand, obviously this is not scaling well to the setting when we have a lot of data and restricted memory. Okay, so next, kernel-based function approximation is related to the previous section. So kernel function can be simply thought of as a similarity metric. So we have some function which given to states S and S prime will produce a similarity metric for these two states. And essentially that is all the kernel is, not really a complicated thing. What it allows us to do, it allows us to use this kernel trick. So when our kernel is of specific form that can be expressed as this inner product, like here, x transposed times x, where x is our feature vector for corresponding states here, S and S prime. Then we can, what we can do, in fact, we can operate in this high dimensional feature space. Like here we have dimensionality of x is d, but using this kernel trick, we don't actually need to go into this high dimensional feature space. Instead, we can just operate in the original space using this kernels. And yeah, so here you can see in this example, we have some datum d, and the value for state S given data will be computed as a sum over all states in our data, where we compute the similarity of two states. So for our state S, we compute a similarity with each of the states S prime in our data, and then we take the value of a corresponding state S prime, and we sum it up. And so in this way, we can, so that would be a kernel regression, as we call it. Okay, I think that should be clear. And a popular choice for kernel function. So here we need some function. Okay, and we need some kind of underlying feature space. So this kernel function might be defined by underlying feature space. So we apply, you can think of it as applying some function phi to state S, and then computing this inner product as given here for this. So the function would project our state into high dimensional feature space. Then we compute this inner product and obtain a value for our kernel function. And the choice of this projection into a feature space is important, and one very popular choice is radial basis function, and I believe it essentially produces kind of infinite dimensional feature space. But because we are using a kernel trick and we do not really evaluate this function directly, we can operate in a high dimensional feature space with manageable computational cost. Okay, so the radial basis function, it was mentioned before. I think we considered in last week as well. It's just a bunch of Gaussians centered, and in this case, before we wanted to use the radial basis function for learning, and in that case we were adjusting the centers, so means and the standard deviations of those Gaussians, but in this case we are selecting them centered on the states of stored examples. So our basis would be static, and yeah, so here we have a non-parametric approach to it. So we just want to compute this this value. Okay, so that's kernel-based methods for kind of memory-based approaches. And again, there is a reference if you want to go into details, and I think there is a lot of information about kernel-based learning and kernel trig. It was very popular, I think, in the 90s and maybe early 2000s due to support vector machines. They are using this kernel trig as a main component, and the support vector machines were really popular, and I think they still are widely used in some applications, but yeah, obviously much less PR for those methods compared to neural networks. And yeah, so still I guess they at this moment they kind of lost this popularity contest, but on the other hand, there are some theoretical works showing the relation of neural net, gradient-based learning of neural networks to the kernel support vector machines. So in some way, the underlying process might be even more similar when than it appears at the first glance. So kind of both approaches are in a way trying to do the lookup into data, but we want to do this in a smart way to compress the data in a smart way to enable good generalization performance. Okay, so they mentioned there are some applications of the kernel trig in reinforcement learning, but they do not go into any details about that. So probably that is not something we will be focusing on. And I haven't heard of solving some interesting problems by reinforcement learning with this kind of approaches. All right. And the last section of this chapter we'll introduce the concept of interest and emphasis. So what that would be. So I think that, yeah, let's introduce the concept, and I think that then it is best understood on this example, for considering the example first, and then thinking about what does it do. So we have some variable I sub t called interest, and it indicates the degree to which we are interested in accurately valuing the state or state action pair at time t. Okay, so if we don't care about this state, the interest would be 0, and if we care about it a lot, then interest would be 1. Or not 1, it can be any non-negative value. So it can be really large. And then we will compute the emphasis m sub t, and it is defined recursively based on the interest at I sub t, and we start with emphasis equal to 0 for all t less than 0. Okay, so we start with 0, and then we just do this exponentially weighted sum of the previous. Yeah, we can say that we kind of accumulate this kind of exponentially interest over t minus n steps, I guess. So we have here some gamma, so that would be our decay factor power n, and we multiply emphasis at time step t minus n, and we add interest at this time step to that. Okay, and now let's look at the example demonstrating the impact of using interest and emphasis during learning. So we have this really simple reward process where we start at this leftmost state, and at each time step we transition to the right until we end up in the terminal state, and at each transition we have a reward of 1. And here we try to approximate our value function with 2 parameters, w1 and w2. So we have this simple state aggregation value function approximation. We have 4 states and 2 weights to approximate those states. Therefore, we cannot compute this values or approximate these values exactly, but we will have to trade off some accuracy at some states in favor of other states if we want to. So here true values are 4, 3, 2, and 1 respectively for all these states, and we transition. Let's assume we have these values for interest. So we care a lot about the first state, but we don't care at all about all the other states. So we want to approximate the value particularly for this first state here. And if we run the Monte Carlo algorithm for this problem without any interest and emphasis, we will, as expected, get the so our W will converge to 3.5 and 1.5 respectively for these two values, and that would be just our average. And that what our like vanilla Monte Carlo algorithm produces. It just produces an unbiased average of these states. In this case, we don't have like all the states are visited equal number of times, and therefore we just have this sample averages, right? So 3.5 here and 1.5 here. But if we run it with these values for emphasis, so our update in this case will be given as follows. So here we have this for an update in this generalized form for n-step temporal difference learning. And here see that our new weights at time step t plus n would be the weights t plus at time step t plus n minus 1 plus learning rate times here we have this our TD error and step TD error, and multiplied by the gradient and multiplied by this emphasis, right? And the emphasis in our case would be like it starts with 0, and then we update it by basically multiplying it by some decay factor and adding this interest. And what it results in that for the learning algorithm with emphasis and interest will converge to the following value that W1 will be 4, which is exactly the value for the first state, for which we have a non-zero interest, and W2 will never be updated, and because we have interest 0 for all the states which correspond to W2. So, okay, that's what the impact would be. And if we apply a two-step semi-gradient TD to this problem, we will end up with W containing 4 and 2. And in this case, we are bootstrapping the value for state, for the first state from this third state. And therefore, the W2 is set to be equal to the value of the third state. So we are starting to care about this state because we are bootstrapping the value for this state using it. And again, the regular algorithm will converge to the 3.5 and 1.5, the averages. And so, yeah, we have this way of basically trading off accuracy for some states to improve the accuracy of approximation for other states we care about most. And probably it can be important for some practical applications when we have this kind of important and unimportant states in our problem. Okay, so that is the end of a chapter, and to summarize, we discussed, like I think we motivated the usage of function approximation for this kind of problems, and very important aspect of it is generalization. We want to get some generalization. So when we are in a state that we have never seen, but it is similar to the states we've seen, we have a good value function approximation for that state. And as you remember, it is not the case with table methods, because in table methods we basically disregard the fact that the neighboring states might be somewhat related when you get the when we are trying to get the value for this state, and we learn a value for each state independently, and then we use it to produce our policy. And that is very hard to apply to most of the real world problems, because the state space can be very large. We can have like some undeterministic environment, and we really want to have some kind of generalization for our learning agent to produce good results. So as we saw, there is a lot of relations with supervised learning function approximation. So basically, we are using very similar approaches as we use in supervised learning, but there are also some differences, and so we are feeding the model our experiences, and in some way that is different to what we have in classic supervised learning, because our experiences are correlated, and yeah, so that might result in some side effects we need to care about during training. But otherwise, we are using the same kinds of architectures or same kinds of methods that we use for supervised learning here. So that should be at least somewhat familiar to those who have worked with machine learning in applications in some space. Okay, and we saw that in general, we try to what we try to do is to minimize the mean squared value error defined in this chapter, and we want to do, and usually we are trying to do this using some semi-gradient method, semi-gradient method, and most of the time it would be some kind of stochastic gradient descent. And we already saw that it has some impact on how our learning approaches work. So for Monte Carlo, we can use a gradient. We can have a true gradient update, and Monte Carlo converges to is guaranteed to converge to some value. On the other hand, when using temporal difference learning, we have bootstrapping, and we are trying to bootstrap based on the value for a function based on its weights itself. So therefore, it has some theoretical problems. The convergence is not guaranteed in all cases, and we saw that we have a proof of convergence for simple linear case, but it might not be true for more complicated function approximation scenarios. But on the other hand, in practice, this is said to work well, and usually TD learning has the same kind of benefits as in TD learning for tabular methods. So we have a better sample efficiency, faster convergence, stuff like that. So, and again, we have all the family of n-step bootstrapping methods for this function approximation, which are between kind of Monte Carlo and TD. So again, we will be using this semi-gradient learning for that. And also we considered a bunch of function approximation approaches. We viewed how can we construct some features for our linear function approximation approaches. Also, we briefly discussed the applications of deep reinforcement learning, where we use a neural network instead of linear methods. And yeah, there are a lot of ways you can approach the learning problem, just as well as in supervised learning. We can instead of using parametric function approximation, we can use memory-based function approximation. So we are storing our experiences and then trying to look up into that to get the value for the state of interest. And so all this can work with reinforcement learning just as well as with supervised learning, but with some differences. So yeah, that's all about this chapter, I guess.
Yep.
Okay, so let's have a look maybe to conclude on these exercises. Okay, one of the simplest artificial neural network consists of single semi-linear unit with logistic non-linearity. The need to handle approximate value function of this form is common in games that end with either a win or loss, in which case the value of a state can be interpreted as a probability of winning. Derive the learning algorithm for this case from 9.7 such that no gradient notation appears. So here we just need to compute the gradient of the logistic function, and that can be done relatively easily. So we will need to substitute here the logistic function which is given in the corresponding section here, and if you remember, the gradient of sigmoid is very simple. I think it's something like 1 minus the one. It would be 1 minus the value into of the sigmoid or something. But yeah, that is you can easily compute it, and it is very simple, and that is why it is. So it is popular for binary classification. So the one of the aspects of it, that the gradient is yeah, really simple here. Okay. And the next, let's check the next exercise. Arguably, the squared error used to derive 9.7 is inappropriate for the case treated in the preceding exercise, and the right error measure is the cross entropy loss. Okay, repeat the derivation of 9.3 using the cross entropy loss instead of squared error all the way to an explicit form with gradient or logarithm notation in it, with no gradient or logarithm notation in it. Okay, so let's check the what is 9.7. Again, this is this generalized update equation, and so here we will need to substitute instead of computing the okay, so that links to this oh, fine, now it makes sense. So here we will use in this exercise 9.7 we are doing the binary classification, right? And before we were using the mean squared error for learning. So if you will try to compute the mean squared error of the output of logistic unit, it will be somewhat complicated. All right, but if you apply a cross entropy loss to it, it combines really nice. So the cross entropy loss will be just yeah, I guess they are, I think there are multiple ways this is defined. I think that in for example, in PyTorch, the cross entropy loss stands for the combination of softmax with negative log likelihood loss, and a sigmoid is a particular case of softmax. You can say that the softmax is a generalization of sigmoid, and therefore the I think that what they mean is using negative log likelihood loss here. And when you use a negative log likelihood loss, it will the problem will become simpler. So the answer here will is it more complex or simpler? It will be simpler, and that is because we have this logarithm in the negative log likelihood loss, and it plays well with an exponential in the sigmoid or in softmax in general, and it will play really not as good with mean squared error loss. But yeah, so it should be simple to derive the solution for this exercise, because the gradient of squared error is simple, as we saw before, and the gradient of sigmoid is simple as well, and you can apply a chain rule here and find a value for that. It will be not too difficult, but the final solution here will be really simpler. And if you're interested in more details on this stuff, I would recommend reading the deep learning book by Goodfellow, and I think they have a very good section on the loss functions and how loss function combine with output units in neural networks. So yeah, I can post a link to it. I think they have the book online, and it's really well explained there. Okay, I think that is all for this chapter, and it was a long one, but the next one will be shorter, and we will talk about on-policy control with approximation. We will have a look at what problems can be related to the, or how do we adapt what we learned so far to the function approximation case. And also in the next chapter, when we discuss off-policy methods, we will see that the off-policy learning in case of function approximation is a bit more tricky. So yeah, a lot of interesting stuff coming up. Okay, so that's all I've got for today. And if you have any points to discuss, please jump in.
No, that was great. Thanks. Cheers, Ardo. Thanks for that.
Right. Thanks, everybody, for joining, and see you next week.
Cheers. See you then. Thanks. Bye.